All right. So the purpose of today's lecture is to talk about RSA crypto system. And we're going to start with where we left on the annual section. But I'm going to do a quick recap just to make sure everybody's on the same page. Napkins. I'm not sure how long this will take. I'm targeting the regular lecture time, 1 hour and 40 minutes, but it might be a little longer or a little shorter, I'm not sure. Lights. Okay. So we've been talking about the modulo inverse. That's critical for what we want to do now. We were saying, last thing we said in class is a at minus 1 exists modulo n if and only if GCD, I say we say capitals, GCD a n equal 1. That's to say, saying no common factors. This is called relatively prime or coprime. Don't be confused with relatively prime or coprime. It doesn't mean those are prime numbers. And then none of them have to be prime to satisfy this property. Just don't have common factors. So we proved this theorem in class on, what is it, Friday? Right? That's what we did. Good. So, now, let me recap another thing that we did, which is the extended Euclid. So how to find, this is existential, so how do we actually find this? We've given two procedures. Option 1 is to build that power set, PA. That was A squared, A cubed, so on and so forth, modulo n. And C, check if some power A at V is 1. If that's the case, then V is called order, and the inverse is A at V minus 1. This we did in class and during the recitations. And if not, there's no power, so if 1 does not belong to P of A, then we say no inverse. This actually was part of the proof of the theorem. Okay, to prove this theorem, we actually computed this power set and we say 1 must be there. If you remember Friday in class, it said if there's no common primes, we build a power set and we show that since powers must be repeating, one of them is 1. The other option was extended Euclid. And Bézout equation. Bézout equation or extended Euclid, not just find the GCD. The GCD is the regular Euclid, but there is a small modification we can do to it to give us more. That is to say, we want the coefficients such that AX plus BY is the GCD of A and B. Usually Euclid just gives me the GCD, but in here I get more. I get this X and Y. And we showed in class how do you modify Euclid to do this. You still go down normally to find the GCD. Once you found the GCD, you go back up little by one, and you from there get the coefficients back. So initially, you get the coefficients from the last row, which is very easy, right? In Euclid, it's something like A, B, Q, R. I start with an A and B, da da da. But the last row is some value, and this is some other value, say T, and this is some quotient, and the R is 0, right? Because that's where I'm stopping. On the last row, I know what coefficients I need, because it's this guy times x plus this guy times y has to be the GCD, which is t, right? So the coefficients I need will be 0 and 1 to get the t, right? In the last row of Euclid, I know the GCD is this value. How do I produce two coefficients that gives me that t? Well, I just pick 0 and 1, right? We remember that from Friday. Now, there is a thingy. How do you go back up with these coefficients? Once you have those here, you need to put them here to get the same, and here, all the way to back to A and B. There's some formulas that allow us to do that. Nevertheless, this is a good, efficient procedure. This in here is debatable how fast it can be for large number, but this is efficient. So we have two ways to find this inverse. And what we want to do now, another piece of recap is this cryptography so far. That's where we're trying to get. I'm going to say linear cipher is you get from an x to y equal x times a plus b mod n. That was the encryption. And the decryption, you want to get it back. So you get x equal y minus b add minus 1 mod n. For this to work, we need a at minus 1 mod n. Otherwise, I can't do the decryption here, right? We've seen this before. What we want to do for RSA, so this is the linear cipher, let me write it here. To do for RSA, we get the message x. We want to do y equal x at some power e mod n. E is public, so anyone in the world can do the encryption. Everyone can take a message and encrypt it. And we want x back to be y at some power d modulo n, where d is secret. So only the people who have that d can do the decryption. Make sense? That's our plan. Now, this is a very powerful cryptographic system in the sense that it's very hard to break. Mathematically, it comes down to some properties that we know are very, very difficult to obtain. So our plan today is to get to the mathematics of this, not necessarily the engineering, but to the math of how does this work? Obviously, like in any crypto system, for this to work, I need this x I get back to be the same x that I started with. Otherwise, there's no point, right? The whole thing of encryption, decryption is to get back the original message. Good. So we need quite a lot of theory to do this. Let me, as a motivation first, show you an example. I didn't have it fully worked out here, but I think we can work it out together. This n, for it to work this way, n has to be a product of two secret and large primes. So this n is PQ. Those are secret primes. Yes?
Is the n also public?
N is public. But not the primes. Okay? So let me show you an example of this. I know we don't have a clue about the math yet, but just operationally, See, the RSA has two parts. Has the setup part. How do you design the whole protocol? Who's P, who's Q, who's E, who's D, da da da, right? Just like in here, right? The protocol has to be with who's N, who's A, and who's B. But then there is the actual mechanics of once it's all set up, how the encryption and decryption happens, right? Once somebody sets it up, the RSA, well, then how the encryption works.
If N is public and PQ are supposed to be secret, wouldn't you be able to find PQ from N?
That's the mathematical hard thing that RSA relies on. If I give you an N and I tell you it's a product of two primes, can you find the primes? We strongly believe that's a very hard problem. So hard that, remember when I mentioned before that some NP complete problems are widely believed to be hard, things like satisfiability and traveling salesman problem and some other problems. Those are the class of NP problems that's big famous and open question in computer science is this class of problems which we know they're all equivalent, easy or hard. Can it be solved in polynomial time? So the big, I don't know if you heard of P versus NP question. This question refers to are the NP known hard problems solvable in polynomial time or not? We know they're all equally hard, and we know if one can solve one of them, it can solve all of them. As examples of this is finding the maximum click in a graph. Solve the knapsack problem, discrete knapsack problem fast. Traveling salesman problem. Finding Hamiltonian cycles, which we talked about. It's also an NP complete problem. Satisfiability, these three SAT formulas, which are the conjunctive normal forms of three literals. What is the assignment to satisfy them? There are many problems that are shown to be equivalent in terms of difficulty. And it's still an open question in computer science. Are all these problems solvable in a reasonable polynomial time or not? Most people believe they're not, because it seems to be that for all these problems, you need to try all the cases, and all the cases exponential. All those problems have the property that if you try all possibilities, you get an exponential running time. Now, that aside, most people believe this is different. So people believe that within our lifetime, somebody will prove that there is no polynomial time to solve those problems. But this has not been proven. It's a famous, one of the top 5 questions in mathematics. If you solve it, or if anyone solves it, you get about $1 million, but there will be nothing compared to the fame of solving this problem. This is one of these things that will make you instantly famous. Now, why I'm saying this? This is not for today. When you talk about algorithms, approximation algorithms, and complexity, you'll study a lot of this. What I'm saying today is factorization, that is n produce the factors. Even if somebody proves unexpectedly that NP is in P, even if we somehow say, okay, we actually were wrong, all these hard problems are actually easy, can be solved in polynomial time. Factorization is still hard. So we don't know how hard factorization actually is, but we know that it's harder than all these NP problems. So we're quite sure that even if, which we don't expect, we expect these NP problems to be very difficult, but even if magically we're wrong and they are actually easy, that's still not proving what she asked. Hey, how about factorization? Decompose n into 2 primes. That's still a very hard problem. So we strongly believe factorization is hard enough that it's not a feasible way to break RSA. Now, of course, it's a cat and mouse game, right? The faster computers get, even hard problems become easier, right? Because we can still do brute force better than we did 10 years ago or 20 years ago, right? Like even if we try to brute force, the typical algorithms you guys know for factorization is try all the factors up to square root of n, right? Try the prime factors. There are better ways than that, but even those better ways are hard. Nevertheless, they can be tried by brute force, like literally try all the factors. So how do we deal with this problem? The more computers become faster, the more we can try more factors, right? Or anything else. Well, we make the numbers bigger, right? Today, it's the typical numbers that are being used, P and Q, are about 2,000 digits. It's RSA 2048, that means 2000 digits. If computers become faster, we make it 3000 digits. Right? So if P is about 2000 digits, or later on, 10 years from now, P might be 3000 digits. Point is, nothing linear in P will ever be feasible. Any algorithm that's linear in P, this is too big of a number. I can write it down, right? I mean, I can write down 3000 digits. Computers can take 3000 digits. But the magnitude of that number makes any algorithm linear in P too slow. So what are the class of algorithms that work for this kind of big numbers? Yes?
Logarithm.
Logarithmic, because logarithm is about 3000, right? So anything like I want to do, like multiplication, find factors, RSA, factorization, you know, like what I need here, E and D, and so on and so forth, everything has to be done in logarithmic time to be feasible. Any algorithm that takes linear time will be infeasible. So I can make, of course, the numbers bigger and bigger and bigger. It used to be 128, then 256, then 512. As the computers become faster, the numbers have to get bigger to avoid the brute force, you know, the farm of computers that are very fast. You could attack maybe 10 to the 64. You could try linear time to break it if you have 1,000 computers that are all like 24 core CPUs and so on and so forth, right? Maybe it will take a year, say, to break that. But once you break it, you have access to all the bank records. So what they did, we said, oh, that's too hard. Well, make it 10 to the 3000. So now, a logarithmic algorithm, instead of 64 steps, will take 3000 steps. That's okay. That run in a few seconds, that's going to run in like a few minutes. But a linear algorithm that has a hope of doing this in, say, 1 year with a gigantic farm of computers, will never finish this if it's linear, right? This is, how many times more is this bigger than that? That's enormous. If this takes, right, the ratio between them is like 10 to the 2900 or something like that. If this takes even a minute, 10 or 29 times that will be forever. Okay? So let me show you an example here. I hope I'm going to get it right. Example. Now, again, our main purpose of today is not the mechanics, but the math behind it. But just to illustrate it, let's suppose I pick P equals 7, Q equals 11. So this is setup. Setup is different than the actual encryption decryption. Setup is figuring out how to publish the protocol. So I pick two numbers. Who's n then? 77. While it's not written here, part of the mechanics of it, there's some numbers that are not being public, even in a secret way, not used, but they're necessary to set it up. So one of these numbers is the phi of n, is the numbers of coprimes or relatively primes with n in Zn. So what I mean by that, who's the relatively prime numbers with n? 1 is of course relatively prime with anything. Is 2 relatively prime with 77?
Yeah.
Right. How about 3?
Yes.
How about 4?
Yes.
5? 6? 7? No 7. 8? 9? 10? 11? No. 12. And who's the next one that's going to be skipped? 14, so there's 13, 14 missing, 15, so on and so forth. So how many relative prime numbers are in Zn with n? We need that. And there is a formula that I'm going to prove today. This number is p minus 1 times q minus 1. So you can count them, literally count those numbers. But instead we can say, well, I know the formula, so how much is P minus 1 times Q minus 1?
60.
Yes. So we need that. And then choose. So this is choose. I pick up those P and Q, prime numbers. In here I choose E, the public E, to be a prime, typically prime, but prime with, it's necessary to be prime with this phi of n. So I can say pick E equal 13. And I need D, which is the secret key. This is the inverse of E modulo phi of n. So that is 13 at minus 1 modulo 60. We need to calculate that, right? How do we calculate the inverse modulo 60? We could either build a power set or do the extended Euclid. So we can try that. Right, some of these inverses, like I said in class, it's hard to guess. It's not that easy. Can anybody guess the inverse of 13 modulo 60?
27.
How much?
No, that was a guess.
Yeah, how much you said?
I said 27.
27 cannot be the inverse because 27 is not relatively prime. Like the inverse, both the number and itself have to be relatively prime with 60. So 27, is it prime with 60? Relatively prime?
No.
What's the common factor?
3.
3. So that can't possibly be the inverse. 27 doesn't have an inverse modulo 60. But it's a good guess. Like, what about another guess?
29.
Hmm? How much?
17, maybe?
17. 13 times 17? How much is it? Let's do it. 130 plus 91, 221. 221 modulo 60. Is it 1?
Okay.
It's not 1, right? I don't know how much it is. Actually, no. It's 180. It'll be 41. You got it?
I think I got the answer. It's 37.
37. Maybe. I'm saying this is not an efficient way to get the inverse in numbers that are even not big. Those are not big numbers. We're not talking gigantic numbers. We're talking about anything that's not modulo 5, 7, 10, something very small. It's not an efficient way to get the inverse that way. How about we get the inverse with the, I think 37 might be the one, but I want to run you guys once through this extended Euclid just to produce the inverse. So instead of guessing it, I'm going to say A, B, Q, R, X, and Y, right? My typical setup. A is who? 60. B is who? 13. Q is who? 4. Reminder is 4 times 13, that's 52, right? 8. Remember, I can't do X and Y this way. I have to go all the way down to GCD to get X and Y back, right? Remember from Friday in class? So what's the next round here? 13? 8. Right? 1, 5, 8, 5, 1, 3, 5, 3, 1, 2. What else? 1, 1, 2, 1, 2, 0. That's the one. Now I knew I'm going to get 1 because otherwise there will be no magic in here, right? If I don't get 1 for the GCD, it's over. There's no inverse, there's no nothing. So now, how do I do the X and Y? I'm also doing the verification here. AX plus BY equal GCD. The GCD will always be 1. So let's see. what x do I need and what y do I need? I said in the beginning it's always 0, 1, right? Because 0, 1 will always work. 0 times this guy plus 1 times this guy will give me 1, which is the GCD. But how do, so as a verification, I get 2 times 0 plus 1 times 1 equal 1. Now when I move in here, I need 3 times 1 plus 2 times minus 1 equal 1. So the coefficients would be 1 and minus 1. I give you guys Friday some formula for how to do this. I don't want to insist on those formulas, they're just mechanics. Just showing that I can go back and get the x and y. In here I need 5 times, it's always the negative 1 moves that way, right? Plus 3 times 2 equal 1. So that's negatives 1 and 2. Then I go, next line is 8 times, would be this 2, plus 5 times, so that would be 2 and negative 3. I'm on the wrong line here. I'm talking about this line. 2, negative 3. Then I need here 13 times, would be minus 3 maybe? Plus 8 times what? 13 times minus 3 is? Negative 39. To get the 1, what do I need?
5.
So those would be minus 3 and 5. And finally, I need 60. The only rule I can remember is exactly what you're doing right now. I remember that this one moves in here. But I don't remember ever the formula for this other guy. But I do it by plugging in, right? I know it's 60 times 5, right? Plus 13 times what? I need to get 1. So this is 300, right? This got to be 299. Can I multiply 13 with something to get 299?
23.
Huh?
23.
23.
Yeah. Well,
Negative 23, right?
Yeah.
So the coefficients I'm getting here, 5 and minus 23. X and y are not unique. So don't be surprised if somebody else, you say 5 and 23, somebody else says some other numbers, you're like, what? These are not my coefficients. That's fine. X and y are not unique numbers. Okay, it's not like in the inverse. If you find it, that's it, because it's unique. In here, it's not like that. You find it, that's good. Somebody else may find different coefficients, they still work. Yes?
So, are there any situations where x and y are unique?
I don't think so. I think it's because if you find an x and y, ax plus by equal the GCD, there's some ah equal same amount to bl. If I find two numbers, h and l, then by adding, the same amount on each side, I still get the GCD.
Okay.
So I think once you found an x and y, you can find a lot of x and y pairs by adding the same amount and get the same answer. I don't want to insist on that, just to give you the answer, x and y, I don't think they're unique. So don't be surprised in Euclid if you are a grader for this class next year. When you get the coefficients from the solution and the student gets a different coefficients, those could be fine. Even here, right? Even at the first line, when we said a times 0 plus b times 1, right, equal the GCD, which is b, the last line. Even here, I think I could have put something else than 0 and 1. Of course, 0 and 1 work. 0 times a plus b times 1 equal b. That's the most obvious thing. But I know that a is b times q. There's no reminder here. The reminder is 0. So the equation I need is a, that's b times q times x plus b times y equal b. right? B goes away with B, it's irrelevant here, B, B, B. So what I really need is qx plus y equal 1. Of course, the obvious way is to say y is 1 and x is 0. But maybe I can find some other x and y here that works. Right? Can I?
X equals 2 and y equals 9.
I don't know. Again, you guys understand what I'm doing. X and y are up to me. I can pick whatever x and y that satisfy this equation. And I say, I can actually pick any x I want. Suppose I choose x 100. Just random number. Can I get a y to satisfy this equation? Yes.
It'll just be, since you have q, you can just do q times 100 minus 1.
Right, so y will be 1 minus q times 100, right? And I make it work. So anybody can pick an x and y. Whatever you pick x, y is just the difference that's needed there to plug it in. I totally agree that the most canonical version is 0 and 1, and that's what I would do, 0 and 1, because it's easy. But you shouldn't be surprised that somebody picks a weird x in here, because you can make it work that way. Yeah, that's a side conversation. So that's how we can find the inverse. So now, if I got this table done, what's my conclusion here? My conclusion is that 60 times 5 plus 13 times minus 23 is 1. Therefore, the inverse of 60, which I don't need the inverse of 60. 60 inverse modulo 13, it's got to be this 5. And the one that I actually need was 13 inverse modulo 60. That's got to be who? Minus 23. Which modulo 60 is?
37.
This is the fastest way to get the inverse. If I've been in an exam and I need the inverse, for whatever reason the exam is asking, I would do extended Euclid. It's the fastest way. And the trick in extended Euclid, to make sure you don't make mistakes, is this column here. One could argue, I don't need this column because I know the formula, I can compute the coefficients. Everybody I've seen and know makes mistakes on these coefficients if he doesn't do the verification column. In fact, if you don't remember the formula for the y, which I never do, the only way is to try to plug in to see what you get, right? You remember the formula for this, you just move the previous y into x, right? And then, how do I know this coefficient? Well, I plug in whatever I need to get 1. So I really need this verification column to make sure I'm getting the x and y's right. And that's what I would do without blinking when somebody asks me about the inverse. Unless there's something I can guess immediately. Well, what's the inverse of 4 modulo 15? It's 4. It's 4 times 4 is 16 and I'm done. If I could do that in my head one time without writing anything on paper, sure. Guessing, it's perfectly valid because the inverse is unique. So once you guess it and you check it, it's good. But if somebody gives me numbers like 97, 143, and like 77, the inverse, I wouldn't bother guessing it. I'll just do extended Euclid. So now we've had the setup done, right? Because we computed the secret key, that is the 37. So the setup is done. We need to be careful what we publish. N is public. That will be who? 77. E is public. That will be who? 13. Is phi of n public?
No.
No. Is D public? No. So we can give E and N to everybody. Hey, here's E and N. You want to encrypt something? Anybody can do the encryption because exponentiation, we know how to do it fast, right? We do the repeated squaring or some other fast algorithm. And we can do exponentiation roughly in log time. So we don't need to do x times x times x in time. Modulo n, so E and N are public, anybody can do the encryption. To do decryption, N is public, but D is not. So somebody would need somehow access to this D to do the decryption. And there's a lot of mathematics beyond what we're going to talk today in class that shows that getting D, unless you are very not careful, there's some particular cases where you can actually get D, but they're very rare and it's easy to exclude them, you know, when E is too small or too high or something like this. In general, it's shown that getting D is as hard as factorizing N. So there is no shortcut in obtaining D easily. In general, so like, unless we have very particular cases that the problem becomes unusually easier, which we know how to avoid, it's proven mathematically that if you want to break this to get D to decrypt messages, it's no easier than factorizing N, which is back to how do we get the prime factors out of a big number, which we know it's a difficult problem. We're not actually absolutely sure, to be honest. We know it's more difficult than NP problems, but we don't know for a fact that it's easy. It's hard to get, like nobody can do it easily. So there's still a theoretical chance that somebody might get factorization done in time. We think that's way too hard. People have tried for many years with computers, with very fancy math, with all kinds of properties. Nobody got anywhere close to it. So for time being, it's safe to assume that security is safe math-wise. When you hear that security has been breached, people have got passwords, they have got accounts, they steal credit cards, they got Facebook messages, whatever. None of these attacks involve even attempts to break the math. Nobody's even trying to factorize N. That's not how people get into your account. That's not how people send messages. Just today, I don't know if you get it, there's a message that appears sent to the dean, Carla Broadley, right? I don't know if you got it. We all got it. And of course, it's not her. It's somebody who broke in and does random things for her email. Most attacks are either a Trojan horse or a backdoor, how it's called, implemented into the protocol or device, right? This RSA will be implemented on some sort of chip or processor or in software. And I could put in there, you know, every time somebody does the protocol, sets up the protocol, secretly I send D to some server, to Virgil server. Right? So I know now that, you know, for your protocol that you set up at IP address and so on and so forth, I record the D because I made that card send the D after it's being computed. Right? That's nothing to do with the math, just listening in. Right? That's how NSA, you remember Edward Snowden and all those stories with the stuff? They had Microsoft and other vendors implementing a backdoor into the devices and into the software. It was not breaking the math, it was publishing the D key or some other ways for somebody who has super access to break in. Another way, of course, is to listen to the password, right? I put a USB listener to your keyboard and I listen to effectively record all the keystrokes. If you ever look at the stream of keystrokes, everything you type during the last week, just record the keystrokes. It's quite easy to see which ones are passwords. Because a lot of stuff makes sense, you know, you type in text, you type in URLs, It's very easy with a parser to identify, hey, this is a URL, this is a piece of text, this is a homework he wrote, this is an email, this is At some point you get this Kabbalistic parentheses and weird signs after the username. That's the password, right? So people have done this. They put a USB thing, especially on desktops. Who checks the back of a desktop? No one, right? So in the back of a desktop, plugging a little USB thing that transmits data around, and nobody noticed the back of a desktop, right? And then they just type it in. Recently, there was some accusation on a Chinese company called Supermicro, maybe you've seen in the news, that when they implemented server motherboards for Apple and Facebook and other companies and Amazon, they put a secret microchip on the board. All it did is to break protocols, that chip, transmitting the data effectively. It says every time you encode or decode or encrypt something, it will transmit the key somewhere. So whoever gets that information has a super access to break in to the main board. Right? All those attacks have nothing to do with the math. They all apart from the math. And as I said, nobody is currently attempting to break the math of RSA. In fact, RSA is a big company today. We had people at Northeastern that work for RSA and they teach cryptography. They developed R in RSA, stands for Ronald Rivers, which is a professor at MIT. So they made this company. The discovery, the whole protocol was 1975 or so, 1980s, and then they make the company. Since then, we study much harder the factorization primality. So we're much sure now than we were then that this is actually impossible or almost impossible to break. RSA is a big company worth hundreds of millions of dollars. And their main, they have two main jobs. One is to study the theoretical problems, how hard is to break those things, how hard is to produce n's, p, and q, and so on and so forth. But the other side of RSA is how do you engineer it? How do you implement it in devices, in software, so on and so forth, so that you're confident it works and confident nobody breaks in. So that's a big security enterprise. Okay, so now we have a setup. If I really want to encrypt something, so now how does it work for in practice? Once I set up and I give the keys to whoever needs them, how do I encrypt? So say x is 10. Encryption will be y equal 10 at power e, which is 10 at power 13, right? Modulo 77. That's how I encrypt my message. Well, I don't really want to compute this, but I guess we could if we want to. Right? How much is that? So how do we do 10 at 13 modulo 77? Yes.
You break it down to powers of 2.
Right. That's a fast way, but can anybody find a way to actually get me a number here?
Calculate?
Right, so 10 to the third, 10 to the square is what? That's how much?
23. 100 not 77 or something.
Right, 23. And then if we square it, 10 to the fourth is, how much is 23 squared? Yes? 529. Okay, modulo 20, modulo 77. That's 77 times 6, maybe? That's 6? Or 7, do you think you fit a 7 in there?
67.
490 plus 49 is too much. Right? So 6. 6 times 77 is? 462. Is that right? Okay, plus what? So 462 plus 38 plus 29. 67? I got it wrong?
No, I did the whole exponentiation in the calculator in one, like.
Okay, how much is it?
10.
Of course.
This is 10?
Yeah. Hiding in plain sight.
That's not good. That wouldn't be.
Is it?
I mean, those things can happen. It's not good because it's exactly the message, right?
Right.
But this doesn't help. This is not actually weak security, right? Because if you get this 10, the only way to cheat is to humanize, if it makes sense, right? It doesn't mean it's easy to decrypt just because it happens to be the same X. The problem here is that if it makes sense in plain. If you hear, okay, the enemy is attacking me tomorrow at 3 p.m. and that's an encrypted message, you say whatever, encrypted or not, it seems like something needs to be checked out, right? I don't know who encrypted this, but this seems like the kind of information that I'm gonna send my scouts to say, hey, is this guy gonna attack me tomorrow at 3 p.m. or not, right? So I mean, if you look at it with human eyes, and if you can make sense of it, but if it's just a number, you know, if you need the number of, I don't know, something in the bank vaults or something, you get 10, you're not going to know if that's actually 10 or not. It still doesn't make it easy to decrypt in that sense. But then if that's true, we will need 10 at D, which is what? So x equals 10 at D, that will be,
It's gonna be 10.
it's going to be 10 again, 10 at 37. Is that 10?
Less than.
Has to be. So you say 10 at 13.
According to Wolfram Alpha, it is 10.
Hmm?
According to Wolfram Alpha, it is 10.
All right. How about we try a different one? Just to make sure we get that this works. What should we try? X. 2 is too small. It has to be prime with 77, otherwise we wouldn't get them to work, right?
I mean, it's just taking it back to the original one.
So how about 15? 15, can anybody do? So y will be 15 at 13 modulo 77. Is that any better than the first one?
64.
64. And then if I do backwards, x is 64 at 37 modulo 77.
7.
What?
64 to the 37 mod 77 is 15.
I'm getting back 15? Yes or no?
I typed it in wrong.
Yeah.
Yeah, 15.
Right. So it kind of works,
Okay.
right? Good. Well, that's what mechanically is happening. Of course, mechanically, when you implement this as a computer scientist, you don't need to check all the math again. You rely on mathematicians that done it. Question is, how do you get it fast, right? You need to, and secretly, like, don't put D in the wrong spot so people can see it, things like that, right? Because people look everywhere. So if you put D in the wrong spot, people will find it. So now, back to the math. Why is this working? That's the obvious question here. I think everybody understood who D is, who E is. There are some choices that I can make. Of course, some are better than others. Things like pick the P and Q, pick the E. Well, there's this magic phi of n, number of coprimes, and then there's the whole calculation modulo phi of n to get E and D. But phi of n doesn't have nothing to do with how mechanically we get RSA encryption. Phi of n is just internal for making E and D work. So before I jump into the math, before I go into, okay, theorem, why the stuff works, I want to show you, for this to work, what is necessary. So for RSA to work, what do we need actually? We need x at E, everything at D, modulo n, to be x, right? Because if you look at encryption, decryption, encryption does x at E, decryption takes that at power D, and it tries to get x back. So that's what we want. And the reason that works is, if E and D, no, if D is the E at -1 modulo phi of n, that's how we got D to work, right? Then we have what? This means E times D equal 1 plus some K times phi of n. That's what it means, right? Because to get E times D has to be 1 modulo phi of n, that means 1 plus some integer times phi of n. So then who's x at ED? Is x at 1 plus k times phi of n, modulo n. And I'm going to say that's just x because there's a theorem that says x at phi of n is 1 modulo n. So if I know this x, I hope everybody can see this is x times x at phi of n at power k. So I'm just saying that's x of 1 because this whole thing here is just 1. Again, why this works? Because x at ED is x as 1 plus k times phi of n. If I know that x at phi of n it's always 1, always, then it's easy. This whole thing is going to be just x, right? But I need this. Yes.
You said x at phi of n is always
1 modulo n. So that has to happen for every x. Every x that's prime with n. X and n co-prime. Of course, it cannot happen like we remember from the lectures and recitations last week. If x is not co-prime with n, when you raise x at any power, remember the power set was a in there, now it's x. Power set will not include 1. So to include 1, you need to have an inverse. And you need x and n to be co-prime. We're back to here. To have an inverse, you need coprimality. So this will never happen if x is not co-prime with n. But in number theory, for this particular n, everything is co-prime with it. Everything that matters. Here's why. X is my message, right? N is a product of P and Q. What kind of x's will not be co-prime? Right, the P and Q are so big numbers. Imagine P 10 to the 3000. The actual message that I'm encrypting is not going to be that big. Right? I'm encrypting a bank account, a password, a name, even a text. If I transform it to ASCII characters and numbers. P and Q are so gigantic numbers that any X that I'm reasonably trying to encrypt is not going to be a multiple of P or Q. And if it is, I can take that as an exception and say I cannot encrypt this number. I can check, is X modulo P0 or modulo Q0. But in general, the X's that I'm going to try to encode are not going to be 10 to the 3000. So that's why I can say for most X's, they are co-prime with them because they're not multiples of P or Q.
So how big does E need to be?
E can be small to facilitate the encoding.
But it can't be like too small. Is that
Right, because then you get this particular case when you can find D.
Yeah.
There's some exercises with RSA that for particular cases, you have to avoid those because you can break RSA that way you can get D back in certain situations. But it's reasonably small that the encryption, it can be instantaneous. Even a cell phone can do encryption immediately. Okay? So, again, why RSA works, we're done. If we could prove this theorem, right? So that's what we need to do today, the main core of the lecture. But before we do, I want to bring back that V order. So I have a... Okay. That's not mine. Anybody forgot their wallet here? I guess you can pick it up now, well, after the lecture. So what we want is X in Zn, GCD of X and N, or A, how I wrote it before. Let's say A, easy. We know there is a V that is the order. So A at V equal 1. Remember that was the theorem on Friday that says if it's coprime you can find the order. But V is the order for A. In other words, if I pick a B in Zn, GCD of B is still 1, B with n, so they co-prime. Co-prime. This is co-prime. There is another order for B, let's call it V2, is the order such that B at V2 equal 1. V2 is the order for B. V and V2 are different powers, or could be different powers. It doesn't have to be the same power. Any element that has an inverse is co-prime, it has an order, but it's not all elements have the same order. Make sense? What this theorem is saying in effect is that there is a common order for everybody. This phi of n is like an order, right? X at that power equal 1. But it's not a different one for different x's. Any x you pick, this phi of n magically works. So how let's try to establish in our heads what this means.
I'm just wondering, is that only true when P and Q are primes, or could it be for any numbers?
X and n, or in this case, A and n have to be co-prime.
Yeah, but what I'm saying is like phi of n is taken from the power set of the coprimes, right?
Right, the size of the
The
co-prime.
size of the coprimes, but is that only true when P and Q are prime?
No,
True.
that's
Okay.
true all the time. We only need it, you're right, we only need it in this particular case for RSA. But this theorem is valid for any n. So this is for any n, and for any x that's co-prime with that n. So n could be not just P and Q, n can be 100 or something. Right? Let's try that. For a general n, we could try this 60 in here, but let's try a general n. How about I pick n equal 20? What are the co-primes? I'm going to say Cn, I'm going to call this set of co-prime remainders. Of course, we know Zn is set of all remainders, but which are the co-prime remembers to 20? 1, it's always there. 2, no, 3,
Yes.
4,
No.
5, 6,
No.
7,
Yes.
8,
No.
9,
Yes.
10,
No.
11,
13.
15, no, 17. Minus 1, it's always there too. So how many? Phi of 20 is how many co-primes reminder I have?
8.
Now, to follow that, pick an x co-prime. So it's got to be one of these. Because this theorem works, it has a constant phi of n, but it only works for co-primes, right? So pick an x a co-prime, I don't know, 7? What is the order? 7 at what power gives me 1 modulo 20? Seven at 2 is what? 49 modulo 20? 9. 9 square again? Is that the one I need?
Yeah.
So that's 4. Observe that 4 divides phi of 20. 4 is a factor of 8. So if 7 at 4 is 1, 7 at phi of 20 will be 1. Because 7 at phi of 20 is a multiple of 4, but 7 at 4 is already 1. So any multiple of 4 will be an order, effectively. If I get 1, 4 times anything will be 1. How about we try another one? 9. 7 at, 9, sorry, 9 at what power is going to give me 1? 2. So the order is 2. But 2 divides phi of 20, so 9 at phi of 20 will be 1. How about 13? 13 at what power I get 1? 13 squared is 169 modulo 20, 9, I'm back to 9. I need 4, right? Is 1, v equal 4. So I've written down the 4. 13 at 4 is 1. 13 at phi of 20, it's also going to be 1 because phi of 20 is a multiple of 4. How about 17? 17 squared is 289. It's 9 modulo 20. So 9 squared is now 1, which means 17 to the 4th is 1. V is 4. Therefore 17 to phi of 20 is 1. So on and so forth. Now you can check the other ones. How about the 19? 19, what will be the order of 19? What power do I need to get 1? 2. Any one of these orders are factors of phi of 20. That's why phi of 20 or phi of n acts like an order for everybody, because while they have different orders, because those orders are a factor of phi of 20, when I raise at phi of 20, I always get 1. That's the core idea of this, which makes this theorem works, which makes RSA work. So let's play more with these factorizations. So the notes for this lecture are in here. It's a number theory part 2 notes. Part 1 is the one that you have to study for exams and quizzes and what else. Part 2 is the one that we're going to do today. We're already doing it. I want to take more of these examples of this coprime stuff. Actually, let me go back to that example a little bit before I do this. You better to do it here actually to see both of them. I give you some examples here. What I really want to say, this Cn, let's look at the power set, for example, who is power set of 7? The 7, of course, 7 squared is modulo 20? 9. 9 times 7? 3. 3 times 7? 1. Right? How about for 9? Modulo 20 is 9. 9 squared?
1.
And I'm done, right? I'm going to get 1. It's the end of the power set because then it's going to start repeating. How about for 13? Is this 13? 13 times 13 is? 9. 9 times 13? 27 plus 90, 117. So modulo 20? 17. And then 17 times 13? Which is 1, right? Modulo 20. And finally for 17, I think for 17 you get the same set because I see 17 in here. Right? If I do P17, shouldn't I get exactly the same set of powers? Well, let's see. 17 squared? 9. 9 times 17? 163?
153.
153, sorry. How much is that? 13. And then 13 times 17 is 1, right? See, I get the same power set. This is the powers of 17. This is the powers of 13. How about 19? What will be the power set for 19? 19, the next one is 1. Is there anybody, what should I do, what power set do I need to get exactly this, but not 7, not for 7? Which one do you think is going to be in here?
3.
Let's see. 3, next one is 9, next one is 27 is 7, and 7 times 3, 1, same. What other power set do you think I'm going to get the same? Can I do a power set for 1? Would that be this? No, power set of 1 is just 1. Is there anybody in this set that you think I'm going to get the same exact thing other than 3 and 7?
Covered everyone.
Yeah.
P of 9?
Yeah,
No, it's just 9 and 1. Right? So once I fix n and I get the set of coprimes right here, I want for every power set like this to create a set of quotients. This is the part that we can't really teach it. Even when the RSA was part of the curriculum, we couldn't teach this quotient. We teach the power sets, but not the quotient. The quotient is saying, I want a bunch of values that when I multiply this times this, I get the whole set. So if I have 4 here and 8 here, how many quotients do I need? 2. 1 will be maybe 1, because I get 1, 3, 9, 7, 1. What are those? I get 1, 3, 7, and 9. Right? And what other number can I put in here that when I multiply those 4, I get the other 4? So I can put anything I want. Can I put 11, do you think? Would 11 do? Well, 11 times 1 will give me the 11. 11 times 3, how much is 33? 13. 11 times 7 will be 77 modulo 60? 17. And 11 times 9 is? 99 is what? Modulo 60. Would 11 work? Will give me the other 4s?
Yeah.
Well, suppose I don't like 11. Can I put something else? I say any one of those 4 we put, we get that set back. We can choose 11, 13, 17, or 19. Any one of them. When I multiply with those 4, I get those back. For example, I can choose 19. How do I get that? 19 times 1 will give me 19. 19 times 3? 57 modulo 60? 17. 19 times 9? 19 times 9? 171 modulo 60? 11. And 19 times 7? Modulo 60? 13. See? I can put anything I want in there, and I get that set. To not get confused, I'm going to put the smallest number possible. So 1 is the smallest, and then what's the other smallest that I can put? Again, to not get confused. 11. So the smallest. Quotient to get all Cn, all the coprime numbers. Of course, I can do the same thing here, right? This Q7, it's still going to be 1 and 11. Because this is the same set, I need the same quotients to produce that set. Hands up, who's with me? How about this? Can I design a quotient set for 9? Obviously, how many numbers I need here? 4. 1 is 1. 1 and 9 will give me who? 1 and 9 here. Now how do I get 3? I put a 3 in here, right? So 3 times 1 will give me the 3. 3 times 9 will give me who?
17.
Really 17? 3 times 9?
7.
7. So I get 3 and 7. How do I get 11? I put here 11. I always put the smallest I can. So 11 times 1 it gives me 11. 11 times 99 gives me? How much? 19. So I get 11 and 19. And how about 13 and 17? If I put 13, I get the 13 times 1. 13 times 9 is? Is it 17?
Yeah.
117, right? 17. See how I get those back? So for every power set, there is a quotient set that if you put the right quotient here times that, you get those values. Ain't that magic? This is easy to see if you know high-level linear algebra. In high-level linear algebra, this is called a group. It has a certain property that means if you multiply 2 of those things, you get a value back in the group. And this in here, it's called a subgroup because the subgroup has the same property. Every time you multiply 2 of these values, you're never going to get out of this group. Anything you multiply here, it's going to stay inside this subgroup. The reason is they're all powers of 7 here. So when you multiply 2 powers of 7, what are you going to get? A power of 7. There's a theorem that says the size of there's always a quotient. If you take a subgroup versus a group, there is a quotient set that allows the subgroup times that to be the group. So that I just applied here in this particular case, but the theorem is general for any group and subgroup, Lagrange theorem. We don't need that. It's in the notes, but that's not needed. I'm only saying this is a general problem of the general property of groups. So if you study some basic high-level algebra, groups and rings and corps and stuff like that, this is a topology phenomena. I want to do the same thing for a different power set. This is all N20. Let's take another one. So the one I have here is N15. Who is the co-primes with 15? 1, 2, 6,
7.
8, 9, no, 10, no,
11.
14. Is that right? So phi of n is 8. Right? It's 8 co-prime, same 8 like before. Now if I take, let's look at here the co-primes. If I do 2, the power set of 2 modulo 15, this is much easier to compute, is 2, who else? 2 times 2, 4, 4 times 2, 8, 8 times 2, 1. Okay. So what quotients I need for 2? To get that set, obviously I get a 1, right? Because if I put a 1 here, I get 1 times 2. I need C15 to be the product of everybody in P2 times Q2 in the following sense. It's any x times y with x coming from P2 and y coming from Q2. It's not a Cartesian product. It's almost like a Cartesian product. What other value I need? I get 2, 4, 8, and 1. What other I need to get the other one? 7, 11, 13, and 14.
7.
7. 7 times 1 is 7. 7 times 2 is 14. 7 times 4 is 28, 13. And 7 times 8 is 56, which is 11. Okay, so suppose I take a different coprime. Suppose I take the coprime 4. Then P4 is going to be 4, and 4 squared is
1.
which is
1.
1. That closes the set, because once I get to 1, I'm done. What's going to be Q4?
1, 2,
Obviously
7.
1. I get 1 and 4. What else do I need? I put the smallest possible. What's the smallest that gives me, say, the 2? 2. With 2, I get 2 and 8. Right? Because it's 2 times 1, 2 times 4. What else do I need?
7.
7. 7 gives me 7 times 1 is 7, 7 times 4 is 28, that's 13. And now I'm left with who? 11 and 14. If I put 11, do I get the other one? Do I get the 14?
Yeah.
11 times 4 is 44, modulo 15, 14. Let's see if I we do one more example, because this is the critical part of the whole lecture today. Let's say I take n equal 26. What is the coprimes modulo 26? 1, 2, no, 3, 4, 12, 5, 7, 9, 11, 13, no, 15, what else?
17.
20, 21 is good? 20, what else? 23 is good? And 25? How many? One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm going to pick a coprime here, say 9, power sets of 9, who's in there? 9, of course. 9 times 9 is 81, modulo 26 is 3. 3 times 9 is 27, modulo 26, 1. So who are the quotients that I need? First of all, how many quotients I'm going to need? This is 12 numbers here. It's 3 here.
4.
I'm going to need 4. The first one is always 1. 1 gives me 1, 3, and 9. Right? Those ones I got. How do I get the 5? I put the 5 right here. 5 times 1 gives me the 5. 5 times 3, 15. 5 times 9, 45, modulo 27.
12, 26.
Modulo 26. Is it 19? 5 times 9, 45. I think it's 19, right? Hands up who's following me here. Okay, what else do I need? I need the 7. I didn't get 7 yet, so how do I get the 7? I put the 7 in here. 7 times 1 gives me the 7. 7 times 3, 21. 7 times 9, 63. Modulo 26, 11. And finally, I'm left with 17, 23, and 25. What do I need to put in here? I put the smallest one of them. So 17 times 1 gives me 17. 17 times 3 is 51. 51 is minus 1, right? 25, and 17 times 9, 153 modulo 26. Is it 23 or not?
This is 133.
Is it?
Yeah, it's 133.
Alright. So I get the Q set. How about I take a different one? I take A equal 5. Who's P5? Modulo 26. 5. 5 times 5? 25. That's minus 1, right? Minus 1 times 5? Minus 5, that is 21. So that's the same as minus 1, it's the same as minus 5. And then 21 times 5, it's 5 times minus 5. That's 1, right? So that's done. Now what's the Q set? The first one is 1, which gives me what these values, 5, 25, 21, and 1. What's the first one I'm missing? The 3. What do I do to get the 3? Put the 3 in there. 3 times this set, I get the 3. 3 times 5, I get the 15. So let's say I got 1. I got here minus 1, that's the 25. I got the 21. And I get the, which one was it? 5?
Yeah.
So now I'm putting the 3. I'm going to get the 3. 3 times 5 is 15. 3 times minus 1 is minus 3. Minus 3 is what? 23. And 3 times minus 5 is minus 15, which is 11. So now what's the first one that I didn't put in? 7. So I put a 7 here. I think I'm going to be done, right? Because 3 times 4 is going to be 12 numbers. So 7 gives me the 7. 7 times 5, 35. 9. 7 times minus 1 is minus 7. And 7 times, what is it? Minus, 7 times minus 5 is minus 35. How much is that?
That's minus 9. Or sorry, which is 17.
So 7 times minus 5 is minus 35, modulo 26.
Which is minus 9.
Minus 9 is this, right?
Yes.
I think by now everybody's convinced that this stuff actually works. Right? Like for every power set, which is what I said in the lecture recitation, what I didn't say, you get the quotient set. And the quotient times the power set gives you the set of the coprimes. It cannot produce anything other than the coprimes, but it does produce all the coprimes. So let's write that down. We have an n, we have an a that's coprime with n. That is the GCD of n equal 1. We have the power set of a, which is a squared, all the way up to 1. Modulo n. And now, who's the QA again? How do we produce this QA? We need some sort of definition. I've done it 3 times already, or 4 times, but how do we produce? We need all smallest quotients required for any, requires such that for any x, any v value in Cn, who's Cn again? Is the set of x with the property GCD of x and n is 1. It's coprime reminders. Is this. We need any v to be v some quotient times somebody in P and A at the power. Right? So we want every, that's how we built it so far. We took every coprime and we said, well, have you got it covered already? If you haven't get it covered, add a quotient such that the quotient times some power of a, which is in PA, is that. So the end result of this definition would be that the coprime set n can be written as a quotient times the power of k, where the quotient is in the Q set, and the power of k, of course, is in the power set. Because that's how we build this set QA. We get the set QA so that every single coprime is the product between somebody in Q9 and somebody in P9. We do it little by little. We first put 1 and we see what do we get. We get 139, okay? What else do you need? Oh, I need a 5. Put the 5 here, so we get now 5 times 1, 5 times 3, 5 times 9. What else do we need? Oh, we need a 7 here. And then we build this set of quotients. Every time I put the smallest possible that I need to cover more elements of the coprime set. The theorem that I need is that the size of Cn, my seems easy, is the size of QA times the size of PA. That's what I want. I already have that every element in this set is the product of somebody here times somebody in here. That's given. Is this now an obvious statement? If I tell you a bunch of numbers are products from here to here, does that mean necessarily that the sets all work that way? In other words, if I put in this Q set another one, so I add to it, I don't know, 9. Would I still have the property that everybody in the coprime set is somebody in P set times somebody in Q set?
Yes.
Yeah, because this 9 times this value is going to be some values in here. Right? So the only way to say that that is true this way is that I don't get any value. I get all of them, but no value gets repeated. So the proof of this theorem, which is done in the notes, it's 3 parts. I'm not going to prove them formally in class, but I'll explain why you need 3 parts. Part number 1, any element V in Cn, there exists, so V can be written as Q times AK. That's trivial. Because we look at Cn, the way we build this Q set Q, everybody who was not a product of a quotient times a power, we put the quotient in the set. So by the time we're done because everybody in Cn can be written that way. So the quotient, of course, is part of Q set, and this is part of the P set. That's easy. Part number 2, once we're done, everybody in here times everybody in here, although we only put the ones that we needed, when we make all the possible products, the values we get are guaranteed to be in here. So in other words, backwards, whatever you pick a Q in the set Q and the AK in the set P, then the product Q times AK is going to be a coprime number. Even though we didn't check all possibilities, right? When we added this 5, we check what we have, but is it possible that we might have gotten something out of Cn? Like in other words, we added the 5, we check 5 times 1, 5 times 3, 5 times 9. Is it possible when we add the quotient here, we make a product, to get some values that are not in Cn? Is that possible? What is Cn again? Is it possible to multiply one of these Q's with one of these A's to get a non-coprime?
No.
Why? AK's are coprimes. And is, yes?
I was going to say, it's because both numbers are coprimes, so that means neither of them share factors with n.
Correct.
And so if you're taking 2 sets of factors that n does not have factors and combine them together.
That's a general property. So for AK, we know that from class, right? AK, it's always coprime because we said yesterday or the other day in class, hey, If A is coprime, any power is coprime. But what about Q? How can you know sure Q is coprime? What was the mechanism to add Q? When did we decide to add this 5?
You pull it from,
Was actually part of the coprime set, right? We look at the coprime set, we say we need the 5, and we said, okay, 5, the easiest way to get is 1 times 5. So because of this 1 here, what we add in the Q set, it's always a coprime, right? If you think about what quotients get put here, those are the numbers that we didn't get so far, like 5, then 7, then 17, right? When I say pick the smallest quotient required, that is the actual coprime that I haven't covered yet. So that's because due to Q and AK are coprimes with N. And part number 3, the last part that we need for this proof, is that if you take 2 different powers in P with 2 different quotients, you do the multiplication, you can't get the same value. So values in Cn as product are not repeated. In other words, if you pick a quotient Q1 times the power of K, any other quotient Q2 times another power, say L, they're going to give different coprimes. For example, pick any value in here in PA with any coprime. 3 times 5 is what? 15. No other product will get 15. So if I pick 1 times something or 9 times something, I'm not going to get 15 again. In here, take, say, 5 times 7, 35, modulo 26, that's 9. The only get to get 9 is this prime times this 7. No other way. Like if I get a 25 or 21 times 1 or 3 or something, I'm not going to get, again, the same thing. So how do we prove this last part? Why is it that if I pick 2 different quotients versus 2 different powers, I can't get the same coprime as a product? Why is that? So the part for number 3, what's the intuition? Why is it that every time I make a product, I get a different value?
Is it because they're all different, they have different parameterizations? So.
How would you prove this by contradiction? Assume it's possible that Q1 times A at some power equal with Q2 times A at some other power, where Q1 and Q2 are from the Q set and AK and AL are from the power set. Why is this so impossible? Yes.
if K doesn't equal L,
Right. Well, if K equal L, Q1 has to be Q2, because I just
Right.
inverted and, right.
So if we assume that K doesn't equal L,
Right, so if K equal L, it's easy. But if K is not L,
then Q1 is going to have to be some
Q2
X.
times A at L minus K.
Right.
So you say L is bigger than K.
Sure. So L is bigger than K, and that means that Q1 has to be the difference L minus K, so that, or Q1 has to equal Q2 times A to the L minus K, and that's a power of A.
Right, this is a power of A, but not Q2. Q2 is not a power of A. What you need to think about here is how did we add quotients to this set? How did we add, let's assume Q2 is the smallest. Q2 is smaller than Q1. How did we add Q2? Because the value was not in there. But then once we add Q2, we'll make the product with, once we say, okay, add the 5 in here, what circles did I put in?
1 around 5.
I multiply the 5 with all the powers, right? And I added those in. So when I put Q2 in, I multiply Q2 with all the powers. Isn't this one of the powers? If I put Q2 and I multiply with all the powers and I check I've got these particular coprimes, I would have checked Q1 in that process. So Q1 will not get to be added as another quotient because it's already getting by Q2. Again, what would that be? If I decide to put a 5, I say, okay, I need 5 times 1. But then I go 5 times 3, 5 times 9, and I select those. So everyone that's already circled will not get in as a quotient because it's not required to be in there. So Q1 will be already obtained from Q2 times a power. I would need to add Q1 to the quotient set. Q1 already obtained as Q2 in Q times A at L minus K, that's in P. So it's not part of the quotient sets. Remember how I added these quotients again? Only the values that were not checked out, I needed to put a quotient in. So if Q1 gives me Q2, it's already in, times the power gives me Q1, I wouldn't need to worry about Q1. Q1 will be one of these already circled values. This may require some time at home to think about it. This is a general property for groups and subgroups. This is just a particular case, but if you don't know this algebra of groups and subgroups, you can just think particularly in this context how it works. If we get to this point 3, we're almost done. So who's with me here? I think those two are very easy properties. Of course, everybody is already obtained as a product. That's how we constructed. Of course, if I get two particular Q and P, then the product is going to be a coprime. Somebody argued that they primes, relatively primes, the product has to be relatively prime. But finally, any product from here to here will give me a different value. There's no way to get the same value on two products. That's the part that's, I would say, definitely hard even for the young students. Now, if you believe all these three, can I conclude that this C is the actual set? If every value could be obtained exactly once, this acts like a Cartesian product, right? Everybody in Q times everybody in P produces a number in C, and all the values are obtained, and all the values are obtained exactly once, then the sizes have to check up that way, right? That's why I get 12 is 3 times 4, or 4 times 3, and so on and so forth. Right? So that proves the theorem that Cn values are produced as all products sum Q in Q times sum AK in P without repetition. So then the size of C has to be the Cartesian size of P A times QA, but the Cartesian size is just the size of PA times the size of QA. Because again, every time you pick a P and a Q, you get the value in C. C is one-to-one mapping to the Cartesian product, but Cartesian product in terms of size, it's exactly how many elements are in P times how many elements are in Q. That proves my theorem, because that means the size of P has to divide the size of C. Who's the size of P of A? Well, how many elements were in P of A? Let's recap who P of A is. What's A, A2, 8 squared, sorry. A cubed. What was the last one we've got? A at v equal 1, right? So what's the size of this set? V. So that is V. Who's the size of Cn? Cn, the size of it is the number of coprimes. Because that C contains all the coprimes. So this is phi of n. So the order of any element that's coprime is a factor of phi of n. Now because A at V equal 1, that implies A at phi of n equal 1 modulo n, right? Because once I get, if phi of n is V times something, k, A at phi of n is A at V at k, which is 1 because A at V is 1. So what did I just prove? I proved that any order that's different for different coprimes, it's a factor of phi of n. Therefore, phi of n acts as an order. Phi of n is order for everyone. Different coprimes have different orders, but all those orders are factors of phi of n. Therefore, phi of n can be thought as an order for everybody. And in the same way, if A at phi of n is 1, where is the inverse? Same way we say for the order. If A at V is 1, previous power must have been the inverse. Can I say the same thing for phi of n? If A at phi of n is 1, where is the inverse? A phi of n minus 1. That means in this case, for example, if I want to compute every inverse, did we do the phi of 26 right here? It's 12, right? If I want the inverse of, I don't know, 11, A equal 11, I want 11 at minus 1 modulo 26. I don't know the order. I could do 11 squared, 11 cubed, right, to get to the V. Or I could just say, I know a grand V that's good for everybody. Who's that grand V? 12. So that's got to be 11 at phi of n minus 1. That is 11 at 11. This 11 power works for everybody. So phi at minus 1 modulo 26, it's phi at 5 at 11. 17 at minus 1, it's 17 at 11. 9 at minus 1 is 9 at 11, so on and so forth. Again, they do have different V's. If you look for the smallest power that gives you 1, it's not the same V. But all those V's are dividers of 12. So every one of these coprime at power 12 will be 1. Therefore, at power 11 will be the inverse. That's a much faster way to compute the inverse, right? Because I need to raise everyone at power 11. Or whatever phi of 26 is, right? So it's not a different V that I need to find. It's a fixed order, phi of n minus 1. So in this case it will be 11. And every coprime raised at 11 will exactly give me the inverse. Raised at 12 will give me 1. So back to my, do I still have that? This is from Friday. Did we erase the RSA here?
Yeah.
Right, so what did we say for RSA? We need x at ED, where 1 plus phi of n times k, right? Some k. X at ED will be x at 1 plus phi of n at k, which is x at phi of n at k times x. If this is 1, x at phi of n is 1, then this is x. This here is a very important theorem. It's here. It's called Euler's theorem. Euler did so many things that so many things carry his name. This is Euler's theorem in number theory. That everyone at phi of n is 1, every coprime, because only coprimes can get to 1. And the inverse, of course, is phi of n minus 1. So that's what makes this particular thing work here. I'm guaranteed that if A and D play nicely the inverse modulo phi of n, then it's guaranteed when I raise x at the power, I get back x. Now, a smaller theorem is in particular when n equal p. This is a particular case. N equal p is prime. Who's CP for a prime? For a prime, what are the coprime reminders? Yes,
Is it all numbers?
except
Or
0.
both? Yeah.
So 1, 2, up to p minus 1, right? So what is the phi of that prime? How many coprimes are there?
P minus
P minus 1. Right? So how do I apply this theorem? I'm going to say any A coprime, but that means any A not 0. Because everything in ZP except 0 is coprime with P, right? Anything other than 0 has no common factors. How do I write this theorem? A at phi of P equal 1, right? Modulo P. Who's phi of P?
P minus 1.
A at P minus 1 equal 1, modulo P. This is a famous theorem. Fermat's theorem. It's called small theorem because he has a much more famous one that's a big theorem. It's just a particular case of Euler's theorem, right? For when n is prime. Because for when n is prime, phi of n is exactly n minus 1. Fermat wrote it A at P equal A modulo P, but that's the same thing. In this case, it also works with 0. I don't have to take 0 out because 0 at P is 0, right? So if I multiply this with an A, I can say it's true for every single reminder, every single number. So that's what Fermat did, and Euler later showed that's a much more general phenomena. It has to do with this set of coprimes. And this is just a particular case for prime numbers where the coprimes are all the reminders. How about, I want another particular case. I'm interested, in a primes this is very easy, but the case that I mostly cared about is not a prime, but the product of two primes. If n is p times q, who is C of n? It's 1, 2. The first one that I'm going to skip, let's say p is smaller than q. Who's the first one that's being skipped here? P. So it's p minus 1, skip p plus 1. The next one that's being skipped? Q minus 1, then skip q plus 1. Then what's the next one that's being skipped? Is 2p or p plus q?
It depends on how big.
P is more than q.
Okay.
It's 2p. So it's 2p minus 1, skip 2p plus 1, right? So what is this? This is the whole Zn minus who? Yes.
Multiples of either p or q.
Right. Any x that is pk minus all every y that is qk. It's all the reminders except the ones that are multiples of p or q, right? So how many are there? Yes.
And there's there's Q multiples of P and P multiples.
So this is inclusion, exclusion, right? Is that how you do it? Inclusion, exclusion principle. How many reminders are in N? N. Minus, you say how many multiples of P are there?
I said there's Q multiples of P.
Q minus,
P multiples, or Q, yeah, P multiples.
but there's a little problem like in inclusion, exclusion. Did we count something twice?
Yeah.
Which one we counted twice? There's only one reminder that we counted as multiple of P and multiple of Q. Which one is that in Zn? PQ is not in Zn?
0.
0.
Which is people.
Which is PQ. But it's not in canonical in Zn, PQ is not in there. Now modulo n, of course, PQ is the same as n, right? This one here is either PQ or, to be more exact, 0. So this is, how much is n? P times Q minus P minus Q plus 1. This is P minus 1 times Q minus 1. Right? That's why in RSA, when we set it up, when we pick the P and Q, we know immediately the phi of n that we need is going to be P minus 1 times Q minus 1. Remember when I said 7 times 11, the 2 primes? What is phi of how many coprimes? We could have counted them, right? Modulo 77, look at all coprimes just like we did in here. But much easier to just say P minus 1 times Q minus 1. Is that, can I do that for 26? How much is 26? It so happens it's a product of 2 primes, right? Which is?
13.
So P minus 1 times Q minus 1 is what?
13.
12. How about, what, did we have another example? 15, right? Did we have 15 somewhere in here? 15 is what? So if I do, instead of counting, how much do I get? 8. Right? I want another particular case because it's cool, not related to RSA, but I like this particular case. What if n is a product, is a prime at the power? What is Cn? Cn is all the reminders again, minus who? All multiples of p, right? So any pk. So how many, this is easier. How many multiples of p are from, what are the reminders? 0, 1, what's the last reminder? P at k minus 1, right? That's the Zn set. Minus 1 down here. What are the multiples? Minus, what's the first multiple?
0.
0. The next one is p times 1, p times 2, up to, what's the last multiple that fits in? P times? Yeah, that's too much, right? Because that gives me p to the k, but I only have p to the k minus 1. So it's the previous multiple, which is this, right? So how many elements are in here again? That's p to the k elements, n. Minus, how many multiples are here?
P to the K minus 1.
So the number of phi of that n is p at k minus 1 times p minus 1. Right? Common factor. Let's try this really quick. If n is 3 to the 3, that is 27. The number, according to this formula, the number of coprimes of 27, coprime reminders, supposed to be who? 3 to the 2 times 2, how much is that? 18. Do you think there's 18 coprime reminders modulo 27? 1, 2, 4,
5, 6, 7, 8.
all the way to 25, 26. Anybody wants to count that? I think there are 18. There is a general formula for phi and n for any natural number. It's in the notes. So these are 3 different particular cases. If p is prime, it's p minus 1. That's very easy to see. if P times Q, that's the RSA case, that's very important for RSA. It's P minus 1 times Q minus 1. And in general, if it's just a product, it's just a P at some power, then it's P at the previous power times P minus 1. But there's a general formula that is phi of n for any number based on the composition into primes. It's very similar with this, but it's for all primes. Not just, this is one prime. If there's another prime, you add it in. This number is critical in number theory, phi of n, the number of coprimes, the size of the coprime set. So the last thing I want to do here is, I hope everybody understood RSA. Let's see if there's some other things that you can read in here, and like very, very useful for number theory. There's one that says Chinese reminder theorem. Very cool thing. Obviously not required for the class. But the last thing I want to do related to RSA is, how do you actually get P and Q? Like the first item, right? How does RSA starts? The setup, not the encryption, decryption. Find P and Q big prime numbers. Well, how do you do that? How do you find P and Q big prime numbers? Hmm?
Just randomize it. Like, how do you know
How?
the numbers you
So
know?
what do I do?
So?
Yes.
Like the sieve vacuum?
What?
Prime sieve?
I can't understand what you
Prime
said.
sieve?
Prime sieve?
Yeah.
What is that?
To find primes with large.
You go by prime after prime after prime, is it? Yeah.
That's not good.
Right, but then once I get to a big prime number, how do I find the next one? I check all the values, P plus 1, P plus 2, P plus 3. I mean, that's crazy, right? We're talking about numbers that are 10 to the 3,000. Yes.
Are there certain formulas that will give you numbers with a high probability of them being prime, such as 2 to the n minus 1?
There are some. There's not an efficient way to find the prime numbers. I like this randomization idea. How do I do randomization to find the
Well,
prime?
I'm sure there's like a library of like.
Yeah, but how is it implemented? I mean, of course there's a program that does it. How does it work?
Does it just have a list of prime numbers?
And then you just randomize a.
Yeah, but how do I find the next one, right? I mean, any list will have to, at some point I'm done with that list, right? If there'll be a list that's relatively small, RSA will be very easy to break, right? Because you give me the name, it's public. I try, division is the same like multiplication, right? Division can be done very fast. If I have a set of candidates P, I divide n with P's repeatedly and I get the Q, right? I check Q being in that list of prime numbers. Whenever I get the Q in that list, I'm done. So it's essential that that list is not a small list or it's a secret list or something, because if I obtain candidates P and I do divisions, I get the Q's back, the whole RSA thing falls apart if I find P and Q, everybody here sees that I can find everything, E, D, whatever else. If I find phi and n, or if I find one of the factors, it's done. So remember, people are very smart, especially adversarial people are extremely smart. Let me make a philosophical argument for that. If you are not very smart in the Western society, it doesn't pay to try to do something against the law. People which are not very smart with enormously high probability will get caught, will ruin their lives for not achieving anything. You want to be a thief? Steal something? If you are not smart, very smart, you very likely better not stealing anything. Because in the Western society, if you follow the legal way of doing things, you're pretty good, right? You can get a pretty good life. You have to be extremely smart and creative to hope to beat the system, right? So people who are trying to beat the system are very smart people and they have enormous resources. So if any sort of, let me put this list because it's a long enough list of primes, maybe they're not going to find it, maybe they're not going to try it, maybe their computer is fast enough, that's going to die very fast, right? So how do I guarantee that even if someone is very smart with a lot of computers, I can't get it to work? I use 10 to the 3,000 numbers, right? But how do I know that number is prime? How do I find it?
Yeah. Well, to know if it's prime, you have to manually check it, because there's no way to find primes and know it's a prime without checking.
So
It's gonna take just as long as breaking.
there are actually rewards for finding large prime numbers, and those rewards are significant, $20,000, you know. It's hard to find them. So here's how they actually do it. We call this, it starts with the randomization. How to find large P prime? Well, randomly generate P with how many digits I need. That's easy to do, right? Just generate 496 digits randomly, one after the other. I mean, that can be done within a millisecond, a little faster than that, right? Generate 4,000 numbers between 0 and 9, which are the digits, is easy. Then I got this enormous number that I need to check if it's prime or not. And I can't use the list or the Steve or the divide all the numbers by square root, because by square root there's so many numbers to divide with, it will be impossible. So then I use an approximative primarily test. Approximative primality test. Here's first what my test is going to do. If my test produces no, it's going to produce A as evidence that A, the GCD of A and P is not 1. So when my test says it's not a prime, it gives me an evidence and say, here's a number that's not co-prime with that. A is smaller than P, of course. And then I know for sure, because they're not co-prime, the P cannot be a prime number, right? Anything less than P has to be co-prime with P if P is prime. Are we all agreeing on that point? When it says yes, actually it's not sure. It's not 100% sure. It's very likely prime, very likely as in not sure, because we couldn't find evidence A. So that doesn't mean it's prime. It means we couldn't find a way to argue it's not prime.
When you say you can find it, do you mean you can find it fast enough? Or you
Right,
yeah.
right. We couldn't find it fast enough. I mean, within the time that's been allocated to me, you know. Try seeing things in a second, 2 seconds, 3 seconds, 10 seconds. The more you try, actually, if you don't find it, the more confident you become, right? If you try a bunch of A's and you can find it, you know. So the primality that's being used is saying A is smaller than P is evidence that this is not prime. Now, again, no, it's for sure. If my prime test outputs no, that's guaranteed to not be a prime. If it outputs yes, it gives me a confidence. Depending how much time I let it run, you know, the more time I give it, the more confidence. It may say confidence 99.993%. And then it's up to me, the RSA designer, the people who made the protocol, do I really want to risk myself with a non-prime that has a 7.007 chance of actually being a prime? Well, if not, I run the primality test another day, and then I let it run for another day or 2 days, and I get 99999 something. This is possible. So it's up to me how much do I want to run it up to I get this confidence higher. Now, there are some numbers that are magical numbers that they pass this test for forever, and they're not primes, right? So even though the confidence increases, those numbers called the Carmichael numbers will pass all the tests, and they're actually not prime. But they're so rare that it makes it, even if, you know, I design a RSA protocol today, by chance I may use one of these numbers because I do primarily test, comes up with very likely prime, I use it. Actually, it's not a prime. Actually, it's one of those Carmichael numbers that pass the test, but it's not a prime. the Carmichael numbers are so rare that's not worth for a hacker to try to attack my RSA system that way. The chance of trying to attack a system like RSA based on a Carmichael number, it's so low. How many RSA? I mean, if I'm a hacker, I need to break a lot of RSA systems, right? Every bank, every human, every computer, everything has a different P and Q and N in there, right? So then, if I break one out of 17,000 RSA systems, that's not useful, right? I need a more systematic way to break it. Yes.
If it's a Carmichael number, wouldn't it just not be able to be decrypted?
What?
Wouldn't it just not be able to be decrypted then?
I don't.
Wouldn't the encryption, like you can encrypt it even though you don't have prime numbers, but would it not be able to be?
No, it will be able to be decrypted. I can use the same. Remember when I say this theorem, it works for any n, not just n times p, n equal p times q.
Correct.
So even if I put p times q times r, 3 factors, or some of the q is not actually a prime number, as long as phi of n is computed correctly and EAD are computed correctly, decryption I think still works.
Wouldn't phi of n be calculated incorrectly in that case though?
Yeah, that's what
Because,
Right. Right. So I think that's true. So phi of n, I computed as p times q, p minus 1 times q minus 1. And your point is if q is not prime, that's incorrect.
yeah.
Right.
So
So-
when you know after you choose the number.
So I can do some tests, I guess, encryption, decryption, when I design the RSA system. I'm actually, to be honest with you, not sure how that works. This is a high-level question. Here's what I think it happens. I do the RSA, I get some confidence that that's a prime number. I don't want to completely know for sure. It takes too long to figure out exactly a prime number. But I can do some encryption, decryptions, take some X's, encrypted, decrypted, right? And if I try, say, 100 encryption, decryption at random and it all works out, maybe that's not the case. This would be broken if Q is not the prime, because for non-primes it's not Q minus 1. Good point. Phi of n computed that way would be incorrect. But again, the chances are so small that nobody's worried about that. Right? I mean, if I put a system like that in place and it doesn't work, I change P and Q, and the second time, imagine if this is a chance of 1 in a million to go wrong. What's the chance of creating another P and Q and get it wrong again? But how does this work? What's the actual test? Right? I mean that's okay. I think we can all agree with an approximation because this doesn't impact industry. But what's the test? Remember, it has to be fast. This is a 10 to the 44,000 digits. You can't run a test that takes time because that's going to be infeasible. So the test relies on Fermat's theorem. Pick an A smaller than P and check A to the P minus 1 equal 1 mod P. What do I know for sure if P is prime?
That this will be true
This has to be true if P is prime.
for all
So when do I declare no immediately?
that. If you find something.
If I don't get 1, right? That will be if A at P minus 1 is not 1 mod P, I can output this A and say, hey, you got something that doesn't work here. If I get 1, 1, 1, 1, 1 all the time, after a while I'm going to say, you know what, I believe that P is prime. But I'm not sure because that's not the guarantee. It only works one way. If P is prime, this must happen. I'm using the converse here. I'm saying if this happens for a lot of A's, P is prime. That's not true, right? So let me just write the converse down here. I'm using the converse if for many A's, A at P minus 1 equal 1 mod P, what I'm concluding is P is prime. This is not true mathematically. I'm testing a bunch of A's, I check that they're all 1 modulo P, and I'm saying if that happens for enough A's, P must be prime. That's not true mathematically, but very likely.
How is this faster though? Isn't this still linear time? Because you're picking the ace in a linear fashion.
Yeah, but I don't pick a lot of A's. I don't pick, you're right, the number of A's will be 10 to the 4 to the minus 96, right? I pick random A's, say 100 or 200 A's. How about the operation itself? A times P minus 1 modulo P.
That's
Would that be linear in P or logarithmic in P? Logarithmic because I do fast exponentiation. I don't need to raise it at P minus. If I really multiply A with itself P times, that's too big. But I can do it in logarithmic time. A's, I can show that for every A I pick, I decrease the chances by a certain amount. So if I pick 100 A's, not all of them, the chances of still being prime and pass all these tests is 1 over 2 by 100, which is a very, very good chance to be prime. So I have here a bunch of numbers as an example. Carmichael numbers. They pass Fermat's primality test, but they're not primes. Extremely rare. So here's examples. 561, which is 3 times 11 times 17. It's a Carmichael number. Any A you pick, you're going to get A at, what is P minus 1? For any A, we get A at 560 equal 1 modulo 561. So it passes all the A's. Even if you go through do all the possible tests, it passes all of them. But 561 is not a prime number. The reason this happens is because 3 minus 1, 11 minus 1, and 17 minus 1 are all factors of 560. That's the actual property of Carmichael numbers. They are a product of a bunch of primes, and P minus 1, Q minus 1, and R minus 1, they happen to divide the number 560. That's why when we use Euler's theorem, when we raise everything at those powers, you get a 1. Here's another one. 1105 is 5 times 13 times 17. Again, every evidence we try to pick A at 1104, it's going to give 1 modulo 1105. That's because 4, which is 5 minus 1, 12, which is 13 minus 1, and 16, which is 17 minus 1, they're all factors of 1104. So perhaps one can exclude Carmichael's number from the beginning because they have a very, very specific structure. I want to avoid numbers that pass all these tests and still not prime. I can check maybe. That gets complicated. Not easy to do this. So there's some examples in here, but of course, you got to take a course in number theory to take it from here all the way to what other things you might want to study. Number theory is a fascinating field of study. It's very much based on reasoning. It's like geometry, you know. It's not, a lot of the stuff you do are pure mathematics, like with not immediate applications in practice. Some applications are found 50 years later, like Riemann hypothesis. It's now known to have implications in analytics and astronomy and other places. But for a while, people have just studied for, even the factorization or NP problems were studied as mathematical objects first without an immediate application, but then people have found out that cryptography can sit on P times Q, and that's how it's actually implemented today. So that's what I have, yes?
Would it be very efficient to like cross-check the result from using Fermat's small theorem with just testing if that P has a GCD of 1 with just random A values?
I think that's inefficient because the chances that such a P will have GCD 1 with random values is quite high.
Okay.
I mean, you can exclude from the beginning simple things like the last digit being even,
Yeah.
right, to not get, you know. But I think this is a more efficient way of doing it. You only need few samples to reduce the probability of being prime to very, very small.
Okay.
By the way, few years ago, somebody do a breakthrough and proved that we can obtain a primality test in polynomial time that's not approximative, it's deterministic. So there is an algorithm 5 years ago discovered by an Indian guy who said, I can prove in polynomial time, I mean logarithmic on bits, that's what it says, it's polynomial in 496, that I can find the primality for sure. I still think, as far as I know, they're still using approximative tests because they're much faster and the probability to fail too small to matter in practice. Even though theoretically this can fail, while this new algorithm from 5 years ago, you can check online. Primality is now proven to be, primality is a polynomial time algorithm to find those. It's not interesting because in practice, this probability is so small and the test is so fast that no hacker will attempt to break it that way. No hacker will attempt to say, maybe by mistake you get a known primes and I break it that way. Nobody will try that. It's inefficient. It's money-wise not worth it to break anything that way. But this was not known for a long time. Now it's known that primality can be solved theoretically in polynomial time. So in principle, one can give up this test and write a deterministic test instead. Alrighty. We can discuss more at office hours if you'd like. Office hours for this kind of things will be on Thursdays. My Tuesdays is regular stuff. Thursdays is more interesting questions. And I hope it's at least some basic introduction into how cryptography actually works. Thank you. Sure. Shut down the camera.
For the keys that you give us, is that like an elegant solution to it?
I don't know.
Because I found sort of a bunch this way.
Is it only one way?
What?
To put it back?
I mean, I just